Hello everyone, my name is Ye. I'm the co-founder of Scroll. Today I'd like to introduce Scroll's design and architecture. Before diving into more detail, for those who haven't even heard of us, what is Scroll? In short, Scroll is a general purpose layer 2 scaling solution for Ethereum. Similar to Ethereum itself, developers can deploy smart contracts on Scroll and also interact with those deployed applications. But the transaction fee is much cheaper and the throughput is much larger. Different from other layer 1 solutions, as a scaling solution, the integrity of all the transactions on Scroll will be verified on Ethereum, either through fraud proof or ZK proof. So the security guarantee of Scroll is much stronger inherited from Ethereum. And more specifically, we are building an EVM equivalent ZK rollup. What does that mean? Now, technically speaking, Scroll is based on ZK rollup, which relies on validity proof to prove all the transactions happening on Scroll are correct. ZK rollup is considered to be the most secure scaling solution based on pure math assumptions. EVM equivalency here means we can support EVM inside with bytecode level equivalency. For developers, it means we can support everything that is supported on EVM, not only a specific programming language like Solidity, but we can support EVM at the bytecode level, and so that we can support all the toolings around. So for developers, you don't need to learn about zero-knowledge proof to deploy on Scroll. The development experience will be exactly the same as Ethereum layer 1. You can reuse all the familiar toolings around and deploy at a similar environment. Before diving into more technical details, let me first describe the principles behind that drives us to our design decisions. The first priority for us is security. So in the context of scaling solutions, the most important form of security is users' fund and their data. We are rooting the security of Scroll in the most secure and decentralized base layer, Ethereum. Users don't need to rely on the honesty of Scroll nodes for their fund security, but instead they can just take advantage of the full layer 1 security, and even when they are doing transactions within Scroll, because your security totally relies on layer 1 Ethereum. And second is efficiency. So in order for user to enjoy a great experience on layer 2, we believe that the transaction fees should be very low, at least order of magnitude cheaper than the base layer Ethereum. And the users should also experience very instant pre-confirmation on layer 2. So for example, like your transaction sent to a Scroll node on our layer 2, you can get a very fast pre-confirmation and also a reasonably fast finality on layer 1, which means your proof gets verified on layer 1 eventually. And third is EVM equivalency. So EVM has a very vibrant ecosystem. We believe that an effective Ethereum scaling solution should give users and developers seamless migration experience from existing dApps and all the tooling support. And EVM equivalency is the best way to achieve this, right? Because you get the same environment. So that's the reason why we want to maintain EVM equivalent going forward, also as our starting point. Fourth is that it's about decentralization. Decentralization is a core property of blockchain that is often overlooked or improperly trade-off for efficiency, especially if comparing for some like layer 1 blockchains, they trade off this for efficiency. But we believe that it's one of the most valuable aspects of blockchains and can ensure protocol and communities are resilient against censorship or coordinated attacks. We consider decentralization across many aspects of Scroll, including the node operator, the provers, and the community of developers and users. So that's what we mean by decentralization across all layers. And those principles actually drive us to our final technical design solution. So the security, efficiency, and EVM equivalency lead to a ZKVM-based ZK rollup solution. So as I mentioned previously, zk rollup provides the best security guarantee. It's based on pure math and instead of any vulnerable economic games. It's also very efficient since the cost per transaction is amortized across a huge batch of transactions. The validity proof has a significant shorter finality compared with fraud proof based on, for example, like optimistic rollups, right? They take almost 1 week to finalize the transaction on layer 1. But for validity proof, as far as you can generate the proof really quickly, you can get finalized because you can verify that validity proof on layer 1. And after the design decision on zk rollup for efficiency and security, we realized that zk EVM is a holy grail to support EVM equivalency in zk rollup. So the idea behind zk EVM is that zk EVM can prove the correct execution of native EVM bytecode using a succinct zk proofs. So, and because previously all the zk rollups are application specific, they are either built for DEX or any specialized transactions. But if you can prove for correct execution for EVM, you can actually make that very general purpose. zk EVM was thought to be impossible due to its large proving overhead. It can be maybe 2 orders of magnitude than normal applications. To make zk EVM practical, we leverage the innovative research-driven solutions from the entire community. Our zk EVM design integrates the recent breakthroughs in proof system, proof aggregation, and even zk hardware acceleration. And our open development approach has allowed us to work with a very broad community members, including especially the privacy and scaling exploration team at ECN Foundation, as well as several other collaborators in this community. We are collaborating very closely on this, leveraging the most advanced research to make zk EVM finally possible. And following all those research results, we are building a zk EVM-based zk rollup to satisfy our design principles. And the next is decentralization. So our requirement for decentralization leads us to build a decentralized pool network first. When designing the whole system, especially zk EVM, we realized that putting EVM into a zk proof requires a very large proving overhead due to the incompatibility between those native fields. And to reduce the proving time, thus, which influence our finality time on layer 1, we decided to build a permissionless and decentralized pool network that helps generate the proof for our layer 2 blocks. So there are 2 major technical benefits for this. One is that our prover is much more like parallelizable and scalable. It means we can massively scale our prover by adding more proving nodes. And secondly, that the community will be incentivized to run the prover and build and substantially better hardware solutions than because they are incentivized to do so. So they don't need to rely on us, which is a centralized party, to build it. Because if you are allow this development in a community way, they can be like even incentivized to build ASICs. Now let's move to our actual architecture design. To give you more context on the whole like architecture, let's take a look back at zk rollup. So Ethereum can process transactions really slowly, right? It can generate block very slowly since it's more decentralized and relies on some consensus mechanism. So instead of sending all the transactions to Ethereum directly, users can send transactions to Scroll. Scroll can generate layer 2 blocks really fast. Then layer 2, our Scroll node will run some proving algorithm and generate a succinct validity proof to prove that a batch of transactions are correct. It will be submitted to layer 1 with some necessary block data as data availability, or in zk proof it's used as public input to prove that after applying those transactions, state 1 move to state 2. So in this way, layer 1 only need to verify the very succinct proof instead of re-executing all those transactions. So the cost can be massively reduced. So to build Scroll, intuitively, we need a scroll node to generate layer 2 blocks, and also a prover to generate proof for those, a batch of transactions or a batch of blocks. So here is the architecture of scroll. It consists of 3 parts: the scroll nodes, the on-chain smart contracts, like the bridge contract is used for deposit and some layer 1 transactions, and the rollup contract is used for verifying proofs and some data availability, and also a decentralized prover network, which consists of a lot of provers. We call them rulers in our system. I will introduce one by one. So first is sequencer. Within scroll node, there is a party called sequencer. It's a fork of Gas. Gas is short for Go Ethereum. So Go Ethereum is the most popular client implementation on Ethereum layer 1. It can be used to accept layer 2 transactions and generate layer 2 blocks. In this way, we can just leverage the existing Ethereum client implementation to make sure that our layer 2 is behaving exactly the same as layer 1, and also give developers a more comfortable way to deploy contracts and not more than just the RPC interface. And second is the relayer. Relayer watches the bridge and rollup contracts and relay messages. For example, like it submits the proofs to rollup contract verification. Like when users are deposited from layer 1, relayer also relay this transaction from layer 1 to layer 2 to process. So relayer basically relays the message between layer 1 and layer 2. And there is also a coordinator which dispatch execution trace to rollers or provers for ZK proof generation. So the execution trace means, so after sequencer can generate multiple blocks, the coordinator will collect those more information, more than just the transaction information from the execution. I will show you later. And because we have a decentralized prover network, the coordinator need to decide who will generate proof for which block. So it will dispatch to different provers. And then this decentralized prover network, which is called rollers, will generate ZK proofs and send back that to coordinator. So basically coordinator sends some information to rollers, and rollers run this ZK circuit, generate some proofs, and send back to the coordinator. So ZK is a core piece of the whole design. So let's take a deeper look at what's happening inside a roller. So firstly, it will receive some execution trace from the coordinator, right? It includes some execution steps, for example, your push, pop, all those steps, all those opcodes you're executing, and some necessary data, your transaction data, bytecode data, and Merkle proofs for elements. And then it will translate into a circuit format using the circuit input builder, which can be used to prove that, for example, because ZK circuit require a different format. So you need to translate from this format to something that ZK circuits can use. And those information will be used as witness for different ZK circuits. So ZK is composed of multiple circuits. Each circuit will be used for one special purpose. For example, EVM circuit is used for state translation. RAM circuit is used for push, pop, those stack-based operations, some memory operations, storage circuit for the whole storage read and write, other circuits, for example, ECDSA circuit for signature, and other circuits. And you will generate multiple proofs. So we will use one aggregation circuit to aggregate multiple proofs into one proof to reduce your final on-chain cost. So for one block or for one execution trace, you will get one block proof. So that's what's happening in prover or in roller. Now let's take from a high level, the workflow of scroll in practice. So a step back for the workflow of ZK rollup, you need to submit the block data and validate proof on layer 1. But actually, block data and validate proof can be separated, right? Because validate proof relies on block data as public input, but block data can be actually submitted ahead of time, right? So we actually have 2 steps. One is submitting the block data on layer 1. The reason is that it's a stronger pre-confirmation because layer 2 block basically tell you no information. You have to rely on sequencer to trust everything. All the information are from sequencer. But once you upload this block data, you can also re-execute transactions. It's a stronger confirmation. So, and then later, at a later stage, because you need a longer time to generate proof, so at a later stage, you can submit this validated proof. So it can make, like your pre-confirmation faster and also stronger. And accordingly, we have 3 different type of status. One is called pre-committed, which indicates that a block has been proposed by a sequencer and included in our layer 2 chain. So this one sequencer includes your transaction, you will be pre-committed. And committed means the transaction data of this block has been posted on the rollup contract on Ethereum. So it's like our blue arrow, like where you post the data on chain. And finalized indicates that the correct execution of the transactions in this block has been proven by this validated proof. Like, which basically means you generate proof and it got verified on Ethereum layer 1. So that means your transaction gets finalized. So here is a graph for how transactions are going on Scroll. So once you send a transaction, you send the transaction to sequencer. And once sequencer generates a layer 2 block, you get pre-committed. So this is for pre-committed block. And the next step is that the sequencer will upload this block data to layer 1, to this rollup contract. And then like you will get committed block. Your status will become committed. And then next stage is that for this block, you will generate some execution trace. And you need this execution trace to generate proof, right? So the coordinator will select some ruler for proof generation. So for example, it select ruler 1 to generate proof for the first block. And then like sequencer for the second block, the coordinator will dispatch this execution trace to a different ruler. And different rulers, they can overlap, right? Because it's different provers and you can generate proof in parallel. And for example, you can have 3 rulers generate proof at the same time. And finally, after they have generated proof, the rulers will send back the proof to the coordinator. And the coordinator will verify the proof and dispatch or assign those proofs to another ruler to run this proof aggregation algorithm. And similarly, it will generate one proof to prove that all the previous proofs are valid. And finally, the coordinator will submit this aggregated proof on layer 1 rollup contract for verification. And this verification contract will take all the previous data and this proof to verify that it's correct. And then your transaction get finalized. So you turn green. So we have rollup explorer show the block status. For example, here your status is finalized and you have committed and pre-committed if you are in other state. So this is a transaction hash for which transaction include your committing, which transaction is committing this data on chain and which includes a proof to finalize your transaction. And we already have a pre-alpha testnet running. You can see with a live ZK proof. So if you want to become an early tester and a contributor, sign up at signup.scroll.io. It's used for interaction with on-chain applications, including bridge and swap. Finally, I want to talk a little bit about our roadmap and where we are. So basically, we already have built a pre-alpha testnet where it's used for it's permission and it can only be used for user interaction. You can play with on-chain applications, and in our next alpha version, we will support more developers to deploy smart contract on us, and then users can play with more different applications. And next stage is that we want to enable layer 2 proof outsourcing, which basically means we want to open this proof generation and make that really accessible to all the community members. It's permissionless and anyone can run the prover and join our proving network. So we use proof outsourcing to refer to this stage. And phase 4 is that we reach our mainnet. So the biggest difference is that it's after more rigorous auditing, more performance optimization, and things like that. And the next stage, we will explore how to decentralize a sequencer, and for example, how to combine some ZK VM modules to our current design to make that more efficient. So We are very ambitious. We set out to onboard the next billion of users for Ethereum because we believe that in the future, all the interactions will happen on layer 2. And also, we are pretty value aligned with the open source community. Everything we have built will be open source, especially for the KVM. We are literally co-building this with a large community from Ethereum. It attracts the best talents who are truly value aligned and make our progress more transparent. Also brings a high security guarantee because you get more external reviews. And we are fighting for decentralization. To enable fully decentralization, we are having a decentralized pool network at our first step. So if you are vision aligned, value aligned, and interested in what we are building, we are hiring. Check out joblevels.co/Scroll Foundation. And we have multiple positionings, and just feel free to reach out if you have any questions. And thank you for listening.